Class, in experiment 5, you'll be applying Le Chatelier's principle. Now, if you remember what Le Chatelier's principle talks about, you will remember that it has to focus on equilibrium processes. So, an equilibrium is a reaction that does not go to 100% completion. So, there will be some reactants left over, and there will be some products left over. So, you can manipulate the shifting of whether reactants or products will be biased based on how you perturb the reaction. So Le Chatelier's principle basically states that whatever you do to the reaction itself will change its equilibrium to counterbalance what you've done, the external force. So you'll be doing 5 reactions in this lab to measure and verify Le Chatelier's principle. The first reaction involves iron plus 3 reacting with the thiocyanate ion. These are in aqueous solutions. And a very important thing to recognize in this section of the lab or in this section of the course is the arrow. Notice the bimodal arrow, the arrow that's going in both directions. So that's a hallmark of equilibrium, and really Le Chatelier's principle is effective in these types of reactions that do not proceed to 100% completion. So if I take some iron and thiocyanate ion, react them together, I'm going to get this complex iron thiocyanate, that has a +2 charge. This is what's known as a complex ion. But I won't get 100% formation of iron thiocyanate. So that is to say, not all the iron plus 3 ferric ion and not all the thiocyanate ion will react. Some of it will react, and some of it will remain unreacted. Hence, this is an equilibrium. I could shift which way this reaction will get biased towards by changing some parameters. And that's what you're going to do in this lab. So this is reaction 1. Well, how do you know which way the reaction is going to proceed when you do this reaction in the lab? Well, fortunately, you have color. This iron thiocyanate is a deep red color. So you can look for the presence of something that's deep red, and you'll know that the reaction has shifted towards the product side, towards the formation of iron thiocyanate, this complex ion. So in 3 test tubes, in test tube 1, you will add some iron nitrate. Okay? So this reaction will be performed. You'll do this reaction first, and then from that reaction, you're going to take some of this reaction into test tube 1, and to test tube 1, you're going to add iron nitrate. So nitrates, all nitrates are soluble. Usually the nitrate is a good spectator ion. But what do you expect would happen if you add iron nitrate, realizing you're essentially, since nitrate is a spectator ion, you're really adding iron plus 3? Where will this reaction shift? Well, the reaction is going to shift towards the product side because you're adding more of this. So when you add more of this, what will the reaction do? Well, according to Le Chatelier's principle, it's going to offset whatever external action you perform. And so when you add more iron plus 3 sourced from iron nitrate, it's going to compensate by shifting to the right. So how do you know that you have a reaction that is shifted more towards product side? You should see a deep red color, or the formation of something that is more deep red. So that is a qualitative assessment. What about in test tube number 2? Asked to add potassium thiocyanate. Okay, so what are you really adding when you're adding potassium thiocyanate to this reaction? Well, you're going to do this reaction, put some of it in test tube number 2. Do that, externally add thiocyanate. Okay, again, just like here the nitrate was the spectator ion, here the potassium is a spectator ion. You're really adding thiocyanate. And when you add thiocyanate, what are you doing? Well, it's the same situation as before, okay? you add to this reaction more thiocyanate ion, the reaction is going to offset whatever external addition that you have added to it. In this case, you add in more thiocyanate. The reaction is going to offshoot and reduce thiocyanate because you added more of it. So, like before, the reaction is going to shift to the right. So here the reaction shifts towards the right, and here the reaction is going to shift towards the right. You would expect a deep red color. Now, test tube number 3 may be a little bit tricky, but it asks you that you will dilute a reaction with water. Yeah, water. So what will that do to this reaction? Okay? So think about this. You're diluting a reaction that's in equilibrium. So what will a reaction do to offset or compensate your external action? What is it that you are doing? You're diluting it, so you're adding water, which is essentially what dilution is. So what would be the offset for this equilibrium reaction? The offset for this equilibrium reaction would be to go towards the side that's more concentrated. Okay? So here, let's example number 3, you add water to this system. The reaction is going to shift to where it's more concentrated. Okay, so it has an opposite effect. So what is more concentrated here, the reactant side or the product side? Well, in the reactant side, I have 2 moles of a reactant, 1 mole of iron plus 3, reacting with 1 mole of iron thiocyanate. And on the product side, I have 1 mole, just 1 mole of product. So which is more concentrated? The side of my reaction that has 2 moles or the side of my reaction that has 1 mole? Okay, the answer is the side of the reaction that is more concentrated is the left-hand side, the side of the reaction that has 2 moles of substances. So the reaction shifts left. Reaction number 2 is going to be a reaction that involves nickel. Okay, so all of these are aqueous solutions, so they're going to be dissolved in water. We'll react with ammonia. Color is actually blue-violet color, so just call it blue here. That reaction has a color that you could use to determine if the reaction is proceeding towards the reactant side or towards the product side. So in test tube 1, you're going to add. So when you add nickel nitrate, what essentially are you adding? Okay, you're adding more nickel. The nitrate is our spectator ion. You don't see any nitrate here, so it's not really playing a role other than to neutralize any excess charge. So you add nickel ion. The equilibrium reaction will offset the addition of the nickel, and we predict that the reaction is going to proceed more towards the Nickel-Ammonia Complex. These are the predictions based on Le Chatelier's principle. Test tube number 2, you will add 6 molar ammonia. That's a pretty concentrated amount of ammonia, so it's probably going to smell like that pine sol or that ammonia smell. What happens to the equilibrium? What are you adding here? Okay, you're adding more of the reactant. The equilibrium will overcompensate or offset whatever you've added, so the compensation will go where? Towards the reactant side or the product side. Obviously, if you're adding more ammonia to a reaction that has ammonia, the equilibrium will move in such a way as to remove the externally added ammonia. We would predict the reaction would shift towards the product side, and you'd have more of a blue color in your test tube. In test tube number 3, you are adding 6 molar H. Okay, so this is an interesting thing. You're adding an acid to a equilibrium between nickel and ammonia. Not just any acid, but a strong acid in hydrochloric acid. So that will immediately react with this NH3, and now you are left with a situation where you have a strong acid coming from HCl with a weak base. All that strong acid will do is really protonate till the end, till all of it is used up, all of the NH3 that's available, and you'll get NH4+. So now you have a side reaction going this way, sort of a reaction that's branched. You have competition, a reaction going this way, and now with the addition of HCl to neutralize this NH3 base, you have a competing side reaction going diagonally in my illustration. So in net effect, what is that doing? The net effect is that you are depleting NH3 by the addition of HCl because it's going to react with the NH3. What does that do to the equilibrium? Well, depleting NH3 causes the equilibrium reaction to shift towards the left or the right. Okay, well, here it's going to shift towards the left, more towards the reactant side. And again, the reasoning being is that the NH3 is gone, the equilibrium will shift towards more production of the NH3 that is in the reactant side. So we would expect a disappearance of blue or less blue here. So notice more of a colorimetric detail, more of looking at different colors. In reaction 3, we're actually going to look at an indicator. The indicator is called Methyl-Orange. I'm going to just call it like that. It has more of a complicated chemical structure, which I don't want to go into. But that's all you need to know. I'm just going to abbreviate Methyl-Orange as MO-, and it's an indicator. You may have seen this in your titration lab in Gen Chem 1, or just plain looking at indicators. You're going to react that with the strong acid HCl, and always put the arrows in both directions. This will give you the protonated version of the indicator. It's still methyl-orange, except it has a proton attached to it, as well as the counter ion Cl-. So all of these are going to be done in water. So this is the medium or the solvent. Methyl-orange actually has an orange color, okay? And this, when you take methyl-orange and add some acid to it, the pH goes down and you have acidity, so the solution becomes more acidic. So the addition of strong acid in the form of HCl is going to cause the reaction to shift towards the right side because you're adding more of the reactant. So you're going to shift it more towards the formation of the protonated form of methyl-orange and the protonated form of methyl-orange. And on the flip side, what happens if you add OH-? Your sodium hydroxide or your potassium hydroxide, any of these strong bases, group 1 or group 2 hydroxides. When you add OH, what does OH do? Okay, so OH is now going to react with the HCl, neutralize that HCl to form water. Okay? So strong acid, strong base, neutralization, you have a competing reaction, and that's a neutralization reaction with a strong acid and strong base. Basically, you add OH, it's going to neutralize or react with the HCl, and you're depleting the HCl as a result of the addition of the OH-. What will the equilibrium do to counteract this effect? It's going to shift to make more HCl, so we would expect the production of MO- to increase, conjugate of HMO, and this has a methyl-orange yellowish color. So the pH is going to go up because the HCl is being neutralized. You have a solution that is more basic, virtue of the addition of the OH-, and O-, the conjugate of HMO, has a orangish yellowish consistency, so yellow-orange. Section 4 in Le Chatier's principle illustrates to us that it also not only just works on aqueous solutions, but it also works, the principle works on solid precipitates as well. So this is going to be an example of this. Calcium ion reacts with hydroxide ion, and it gives you a precipitate of calcium hydroxide. So this is a solid, it's a precipitate, it will crash out of solution. By crashing out of solution, I imply that it's going to form a solid blob or solid precipitate. Notice my states, solid, aqueous, and aqueous. And notice that I may have a counter ion associated with the calcium. I may have a counter ion associated with the hydroxide group, but it's the calcium ion reacting with the hydroxide ion, forming calcium hydroxide. We call calcium hydroxide sparingly soluble, and the reason why it sometimes gets that moniker is, again, by virtue of that double arrow. It does not proceed to 100% completion. In this equilibrium, well, in one scenario, when you do this reaction and you filter out precipitate, you'll take some of that precipitate and put it in test tube 1, mLs of 6 molar HCl. What do you expect to happen to this Equilibrium, when you take some of that precipitate and add 2 mils of 6 molar HCl. Okay, 6 molar HCl is pretty concentrated, taking 2 mils of it. So what will happen? That produces immediately a side reaction because that HCl is going to react with our hydroxide. That's a neutralization reaction. Strong acids, strong bases predominantly shift towards water. Very little of it goes back. And so now we have a competing reaction. We have a reaction that's going this way, and now we've set up a system by the addition of molar HCl, 2 mils of that. We're setting up this reaction. The net effect is that this OH minus is going to get depleted. The reaction is going to shift towards the product side. It's going to shift towards the reactants or towards the left. So we actually would expect less precipitate. Or, in other words, you can say that the addition of 2 mils of 6 molar HCl to this precipitate actually dissolves the precipitate. Flip side happens if you do the opposite. Happens if you, to this precipitate, added acid. To this precipitate, you add base. Add, according to the directions in the protocol, 5 mils of 6 molar NaOH. What do you think is going to happen to this precipitate that you've set up? You're adding more OH minus. It's going to be the opposite scenario as in situation 1. Here you're adding acid. Here you're adding more of the reactant in this equilibrium. So what will the equilibrium do to counteract your addition of base? It's going to shift the reaction towards the right. And we should expect more precipitate, more calcium hydroxide precipitate, forming by virtue of adding more OH minus. Again, the sodium ion is a counter ion here, spectator ion, just like the Cl minus ion is a counter ion or a spectator ion here. The final thing you wanted to look at here in this lab is heat. So our discussion of heat primarily entails whether a reaction requires heat, that would make it an endothermic reaction, or whether the reaction in question pulls heat or gives off heat from the system to the surroundings. In that situation, we call that reaction exothermic. Cobalt in aqueous solution actually has a pink color, and that's going to react with some Cl minus. It's also an aqueous solution. This will have its counter ion. This would have its counter ion. But we're really interested in these 2 ions in aqueous solution reacting. Look at my arrow and always take note of the arrows. It's going to form this complex ion. Salt tetrachloride with a -2 charge. I do not know the exact name of this inorganic complex ion, but we'll just call it a complex ion tetrachloride with a coordinated to cobalt. This reaction actually has a blue color. Now, to add a little kink to this, we actually want to know whether the reaction is endothermic or exothermic or not. So this is where you're going to have to look and see if the reaction is going to require heat or, scenario 2, evolve heat. In this case, heat would be a product. What is it? Is it going to be endothermic, the formation of this complex ion, or is it going to be exothermic, the formation of this complex ion? You determine that? One thing that you can do to determine that is simply add heat. You can raise the temperature. When you raise the temperature of the system, what do you expect to happen if the reaction is endothermic? If the reaction is endothermic, heat is a reactant, in this case for an endothermic reaction. So when you add heat by virtue of raising the temperature, this reaction is endothermic. That's what you're going to have to find out. You would expect more blue formation. That is by virtue of the fact that you add heat and the equilibrium offsets your addition of heat by making more of the complex ion. Maybe it's not endothermic. Maybe it's exothermic. You can do in scenario 3 and remove heat. In this case, you can lower the temperature. If you lower the temperature, it results in, so if you remove heat and the reaction is exothermic, move this reactant, reaction is going to shift more towards the part that got lost. What happens if the reaction is exothermic? If the reaction is exothermic and you add heat by raising the temperature, you should actually see the reaction shift more towards the left-hand side. So if the reaction is exothermic, have a pink color. If you remove heat and the reaction is endothermic, if the reaction is endothermic and you remove heat, then you remove this from the reactant side because it's an endothermic reaction. The equilibrium will adjust to shift towards the reactant, and then you would have a pink color. With deionized water, as we stated and alluded to before, the net effect to countervail the dilution is to go to the side of the reaction that is more concentrated. So here you have 2 moles on the reactant side. Here you have 1 mole on the reactant product side. So the equilibrium will shift to whichever side is more concentrated.